तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we were considering the Fourier transforms of functions of time f of t, which are not absolutely integrable over the infinite range. To do this, we laid down certain formulas which we can assume. These formulas can be justified on the basis of distribution theory, and we will just assume these formulas in deriving these Fourier transforms of these special functions. Special in the sense that f of t is not absolutely integrable over the infinite range. To start with, we took the case of a pure DC. So, if f of t equals 1, then we set the Fourier transform for this f of j omega is 2 pi delta omega. The spectrum, Fourier spectrum, then will comprise just a single impulse at the origin in the on the omega axis. Since this time function now is a pure DC, we cannot expect to have frequencies at any value other than omega equals 0, and at that point you have a definite non-zero coefficient in the Fourier series expansion for f of t, which is equal to 1, and consequently you have a density, Fourier coefficient density, which is infinitely large. And since the Fourier coefficient density is defined in terms of the coefficient for cycles per second, since we are plotting this on the base of omega, it turns out to be 2 pi delta omega. The concentration is 2 pi times delta omega. Now, let us extend this to a sinusoid. Suppose I have f of t as cos omega ct, a sinusoid of frequency, angular frequency omega c. This of course can be written as e to the power of j omega ct plus e to the power of minus j omega ct divided by 2. So, in other words, f of t consists of two exponential functions, half multiplied by e to the power of j omega ct and another half multiplied by e to the power of j omega ct. Now, the difference between half e to the power of j omega ct and f of t equals 1 is that it is no doubt scaled down by a factor 2, but the time function is multiplied by an exponent e to the power of j omega ct. We had earlier discussed the property of the Fourier transform. If f of t and f of j omega form a transform pair, if f of t is multiplied by e to the power of j omega ct, it means in the transform domain the frequency spectrum is shifted. E to the power of j omega ct times f of t has a Fourier transform which is f of j omega minus omega c, a property which we have studied earlier. So, we will make use of that property, and therefore, the Fourier transform for this will turn out to be first of all scale factor half is there. So, if f of t has a transform 1, f e to the power of j omega ct has a transform 2 pi delta omega minus omega c. Likewise, for the other term you have 2 pi delta omega plus omega c. Which of course is pi times delta omega minus omega c plus delta omega plus omega c. So, what do we have? A pure sinusoid here, a cosine function goes like this. This is f of t. As far as the transform is concerned, you have f of j omega. You have one impulse here, another impulse here at omega c on the positive side and minus omega c on the negative side, each of strength pi. So, what we observe here is, once again this is a pure frequency term, that is only one single frequency is present, a pure sinusoid cosine omega c t, and therefore, the energy is concentrated only at two discrete frequencies as far as in the exponential representation. They are in sinusoid. If you e to the power of j omega c t and e to the power of minus j omega c t, there can't be any energy at any other frequency, and these two terms together constitute one sinusoid at frequency omega c. So, this is quite revealing that even a pure sinusoid or a pure DC can be represented by means of a Fourier integral in this Fourier transform in this manner. Let us extend this idea further. It can be shown that if you have sin omega c t, which of course can be written as e to the power of j omega c t minus e to the power of minus j omega c t by 2j, obviously this Fourier transform by the same arguments as before will be pi times 2 pi times delta omega minus omega c plus minus corresponding to the second term you have 2 pi times delta omega plus omega c. So, this will be minus j times pi minus j pi, I can take that as a common factor, delta omega minus omega c and minus. So, it is a pure sinusoid, therefore, you have a sine wave extending from minus infinity to plus infinity, and for the Fourier spectrum you have magnitude spectrum, you have magnitude, we have as before two impulses at omega c and minus omega c, each of strength pi, and the angle of f of j omega will be for the frequency omega c and minus omega c. These are the components that are present only at these two frequencies. When the impulse at omega c is minus j pi, therefore, it is minus 90 degrees, and at this plus 90 degrees, therefore, this is pi upon 2 and this is minus pi upon 2. So, this is the angle spectrum, phase spectrum, and this is the magnitude spectrum. Now, why do we stop at this point when you are, after all, you are now able to find out the Fourier transform of a DC, a pure sinusoid. One can as well go to the extreme case of a pure of a non-sinusoidal periodic function, and indeed it can be shown that a non-sinusoidal periodic function which admits a Fourier series can also have a corresponding Fourier transform. Let us see how it goes. A general periodic function. Suppose f of t is a periodic function which admits the Fourier series representation in this manner. N from minus infinity to plus infinity. So, this periodic function is something which repeats itself at regular intervals with a time period t naught, and omega naught being 2 pi over t naught. So, that is a fundamental frequency. Now, we have seen that a constant will have a constant will have a Fourier transform which is 2 pi times delta omega times that constant. This is 1, therefore, this is 2 pi times delta omega. Now, each one of these terms in the Fourier series expansion will therefore have a corresponding Fourier transform, and the summation of all those transforms of individual components will be the Fourier transform of the entire function. So, it is from the discussion it is quite obvious that f of j omega will be equal to for this term C n, of course, you have 2 pi times C n. If it is C n alone, it would have been 2 pi times C n times delta omega. Okay. But you have e to the power of j n omega naught t, therefore, this becomes delta omega minus n omega naught. And you have all such terms starting from n from minus infinity to plus infinity. So, that is its Fourier transform. So, a periodic function of time which has a Fourier series also has a corresponding Fourier transform. Now, the Fourier transform of this would have a magnitude spectrum like this, f of j omega. Let us see, at DC it will have 2 pi times C naught, at omega naught it has 2 pi times C1 and so on and so forth. At minus omega naught it will have 2 pi times magnitude spectrum is even spectrum 2 pi C1, and you may have at 2 omega naught 2 pi C2. These are the strengths of these impulses. Pi times C2, etc., etc. Now, if you plot the Fourier spectrum of the Fourier series in the conventional sense, what you would have done is the spectrum of the Fourier series, what we talked about the spectrum, what we talked about spectrum in when we were discussing the Fourier series, you would have plotted a line spectrum like this, C1, C naught, C1, C2, C1, C2, etc. This is the magnitude spectrum of the Fourier series. Magnitude spectrum of the Fourier series. Now, what we have in the case of the Fourier transform is, instead of these being the coefficients, we have impulses. So, instead of finite constants here, we have impulses. The strength of each impulse is 2 pi times the corresponding coefficient here. Therefore, this is the Fourier magnitude spectrum of the Fourier integral in the sense. This is the magnitude spectrum of the Fourier transform or integral. So, we have now seen that a Fourier integral gives a more generalized concept of finding out the various harmonic components of a time function of time. It can be used not only for aperiodic functions, but periodic functions as well, because once we have the Fourier series for a periodic function, in the Fourier transform domain, all it means the same line spectrum is carried over into the transform domain as well, but instead of coefficients, finite values of coefficients, you have impulses, each of which has a strength which is proportional to the Fourier coefficient. And since this particular waveform has frequency components existing at 0, omega naught, 2 omega naught and nowhere else, here also in the coefficient density you have concentration of energy at these particular frequencies and nowhere else. So, it is not a continuous spectrum now, because the f of t turns out to be periodic, not only here, 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 and even in the case of DC can be considered to be a periodic function. So, the conclusion that we get is, whenever we have a periodic function of time, then the spectrum will turn out to be a line spectrum. Let us now continue with our discussion and derive some additional Fourier transforms of functions of time which are not once again absolutely integrable over the infinite range, but at the same time they are not periodic as well, like the cases we have just now considered. To start with, let us take the unit step functions. U of t. This of course has a value 1 for positive t and 0 for negative t. U of t is the unit step function in this sense. Now, you would like to find out the Fourier transform for this. So, f of j omega 1 over 2 pi integral from minus infinity to plus infinity of f of t e to the power of minus j omega t dt. And since f of t is 0 for negative values of time, you can start the integration from 0 to infinity of f of t is 1 in that range. So, you have cos omega t minus j sin omega t dt. Minus j sin omega t dt. And from the formulas which we have developed earlier, this is seen to be pi delta omega, the formulas which we noted down in the last lecture, and this will be minus j upon pi. So, this will be pi delta omega plus 1 over j. This is the Fourier transform of a unit step function. So, if you plot the spectrum, there will be an impulse of magnitude pi sitting at the origin, and you have a continuous spectrum of decreasing amplitude as omega increases corresponding to 1 over omega. So, that will be the magnitude spectrum that we have. Now, look at this. This particular function of time u of t is neither even nor odd. Therefore, we cannot expect the Fourier transform to be either purely real or purely imaginary, and indeed it has got a real component and a purely imaginary component. So, this unit step function therefore has a Fourier transform which is pi delta omega over 1 over j omega, and let us see how we can sort of justify this. Or we know that a unit step function is obtained by integrating a delta function, or in other words, a unit impulse function is the derivative of the unit step function. And since we know the rule for the derivative of f of t, how it gets transformed in the transform domain, let us see how both these relationships are related to each other. In fact, we know that delta t is d by dt of ut. Therefore, we would expect that the Fourier transform of delta t will be obtained by multiplying the Fourier transform of u of t by j omega, the j omega Fourier transform of u of t. So, you take the Fourier transform of u of t, multiply by j omega, you must get the Fourier transform of delta t. On this basis, we conclude the Fourier transform of delta function is 1, and this is j omega times Fourier transform of u of t. If this is so, the Fourier transform of u of t, can we conclude from this divide everything by j omega, can we say this is j omega? If so, then if u of Fourier transform of u of t is 1 over j omega, then that is not in accordance with what we have just now derived. So obviously there is something inconsistent here. The steps here also seem to be in order, but the catch here is whenever you are dividing by j omega, you must also take in possibility of a delta function being present. In fact, if you have j omega times 1 over j omega plus some k times delta omega, suppose I have an impulse of magnitude k sitting at the origin, if you multiply right through, you have 1 plus k j omega times delta omega. And whenever you multiply a function f of omega is multiplied by delta omega, that f of omega can be replaced by f of 0, because after all this delta function here has value at omega equals 0 only and nowhere else, and therefore the value of this function at omega equals 0 is the only one that matters, and in this case kj omega equals 0, therefore this is equal to 0, equal to 1, this is equal to 0. So in other words, j omega multiplied by this is equal to 1, therefore if you take 1 over j omega, it could be 1 over j omega plus k delta omega as well. So that is where we have a discrepancy here. This is of course true, but it is not a general expression. The general expression for this would be f of j omega. From this it follows that the general expression for when you want to solve for this, f of u t must be Fourier transform of u of t. The most general way in which this equation can be solved is to write 1 over j omega plus k delta omega. So this is a, whenever you are dealing with impulses, one has to be careful in this manner. In the algebraic solution of equations, when you divide by j omega, you must also take into account the possibility that there is a delta function is there, because if you multiply this by j omega, it is equal to 1. The second term drops out. Okay, having agreed to this, now what is the value of k? How do we get the value of k? In the earlier derivation we saw that k equals pi. So how do we justify this pi from this reasoning? Now let us see. Assuming that Fourier transform of, assuming this relation, assuming the above relation, let us calculate u of t. U of t therefore must be, so assuming the above form, we can obtain u of t through the inverse Fourier transform formula, which is 1 over 2 pi minus infinity to plus infinity of f of j omega, which is 1 over j omega plus k delta omega e to the power of j omega t d omega. That is the inverse Fourier transform formula. Right. Now in this formula, let me substitute the value. After all, this is a function of t, this is a function of t. Let me substitute the value of t equals 0 in this. Now what is the value of u of 0? I ask this question. And on the other side, I substitute t equals 0. Therefore 1 over 2 pi minus infinity to plus infinity of 1 over j omega plus k delta omega e to the power of j omega t now becomes 1 d omega. Now we observe carefully the expression on the right hand side. D omega by omega is an odd function of omega. 1 over omega is an odd function of omega, integrating between symmetrical limits from minus infinity to plus infinity. So the positive and negative areas cancel themselves out, and therefore the contribution of this term 1 over omega d omega, whatever it might be, will be 0, or whatever it might be on the positive side and whatever it might be on the negative side, it is going to be 0. So the only contribution that comes from with this is from the second term, and when you are integrating from k delta omega over the infinite range, that infinite range covers the where the impulse function stands, and therefore this will be simply k over 2 pi, because integral from minus infinity to plus infinity of delta omega d omega equals 1, therefore k by 2 pi. But what is the value of the step function at the origin? You recall from the Fourier series theory, we said whenever there is a discontinuity of any function, the Fourier series converges to the average value of the limit you get from the starting from the right side and the left side. So in other words, here also u of 0 minus is 0, u of 0 plus is 1, therefore u of 0 at the point t equals 0, this will turn out to be half. This is how the Fourier transform and Fourier series, both of them converge. And since u of 0 is half, and that must be equal to k upon 2 pi, k equals pi. And that indeed is the value that we had obtained here. So this is how it be tied up with the formula that we have obtained, starting from the Fourier transform of the impulse that we know already. Now let us look at it from another angle. Let us say another viewpoint. We can always think of a u of t to be the sum of, suppose there is a pure DC term half. What else should we add to that pure DC term to get this? I must add to this a function which has a value of half for positive t and minus half for negative t. If I add these two functions of time, I would indeed get this unit step function, because on the negative side this area is cancelled by this area, and the positive side both of them both these values add, so it will be plus 1 for positive t and 0 for negative t. Now we know that the Fourier transform for this, a pure DC, if it is 1 it would have been 2 pi delta omega, but this is half, therefore this pi delta omega. And we know the Fourier transform for this we have just now derived is pi delta omega plus 1 over j omega. So it would appear that the Fourier transform of this should have been 1 over j omega. So we have a unit step function can be resolved into two functions, one a pure DC and another which has an odd function of time, which has a value half for positive t and minus half for negative t, and this is an odd function, therefore its Fourier transform is a purely imaginary and everything ties up nicely, and therefore it appears as if that a function like this which has a negative value for negative t and an equal and opposite value which is the positive value for positive t has a Fourier transform of this type 1 over j omega. And this is a type of important function that appears again and again. So we will try to derive this the Fourier transform for such functions independently, that is what we will do next. But now we can see that a unit step function consists partly of a pure DC and partly of a function like this. We just now saw that an interesting function which has constant for positive t and constant for negative t, but the two constants are negatives of each other. A function like this is defined as a Signum function and is usually symbolized like this. This is Signum function of t denoted as sg and t has a value 1 for t greater than 0 and -1 for t less than 0. And such a function will have a time variation like this. This is called Signum function. So, obviously, its Fourier transform can be derived in the usual way from -infinity to 0. Its value equals -1. Therefore, I will write this as minus e to the power of minus j omega t dt. And I split up this integration into two parts, -infinity to 0 and 0 to infinity. 0 to infinity, its value equals 1. Therefore, 1 times e to the power of minus j omega t. Now, I can put t equals minus x. If I do that, it will be minus of e to the power of minus j omega t equals minus x. Therefore, I can write this as plus x j omega x, and dt equals minus dx, and the integral limits will become infinity to 0. My idea is to combine these two terms in some fashion and put them between the same limits of integration, 0 to infinity of e to the power of minus j omega t dt. Now, in this integration, x is a dummy variable of integration. I can reintroduce t, and then I notice there is a negative sign here and a negative sign here. Therefore, they cancel each other out, and I interchange the limits of integration. Therefore, there is another negative sign coming. Therefore, this becomes 0 to infinity minus of e to the power of j omega t dt plus 0 to infinity of e to the power of minus j omega t dt. We can combine these two as 0 to infinity of e to the power of minus j omega t minus e to the power of j omega t dt, e to the power of minus j omega t minus of e to the power of j omega t. It will be 0 to infinity. This will be minus 2j sin omega t dt. Minus 2j sin omega t dt, and minus 2j can be pulled outside the integral sign, and what is left with 0 to infinity of sin omega t dt. And this integral has a special value which we indicated in the last lecture, that will be 1 over omega. Therefore, this will become minus 2j over omega, or I can write this as 2 over j omega. So, the upshot of this is now that to say that the Signum function of t minus 1 plus 1, that is Signum function of t, has for its Fourier transform 2 upon j omega. Of j omega. And therefore, when we had in the derivation of the unit step function, you recall that once again, let me redo what we had done there. The unit step function can be always be thought of as 1/2 plus 1/2 of Signum function of t, because if you add a pure DC of magnitude half and a Signum function which has minus half and plus half for negative and positive times, then the sum of these will indeed result in u of t. And therefore, the Fourier transform for this, from the DC part you get pi delta omega. It is an even function, therefore, this is real, and for the Signum of t you got 2 over j omega, but since we have a coefficient half here, this will be 1 over j. So, that is the Fourier transform. So, a Signum function can be represented in this fashion, and it has a Fourier transform which is 2 upon j omega, and so what we earlier said 1 over j omega corresponds to a function of this type. We wondered if that is so, then it is justified now based on this particular analysis. Okay. Now, you also observe that it is a purely odd function of time, therefore, the Fourier transform turns out to be purely imaginary. Okay. Now, let us take next a truncated sinusoid. What we are really mean by this is, suppose we have a function which is only lasting for positive t. So, we are taking cos omega c t u t. That means, for the negative values of time it is cut off. This we are calling a truncated sinusoid. To find out the Fourier transform for this, we recognize that this is equal to half of e to the power of j omega c t plus e to the power of minus j omega c t times u of t. Now that we have the Fourier transform for u of t, we can find out the Fourier transform of u of t multiplied by e to the power of j omega c t and e to the power of minus j omega c t. So, this will be, we know that u of t has for the Fourier transform 1 over j omega plus pi delta omega. Now, we have u of t multiplied by e to the power of j omega c t, which means instead of omega we have omega minus omega c and delta omega minus omega c. It is also multiplied by half. So, we take that into account. Similarly, u of t is multiplied by e to the power of minus j omega c t. What it means is the Fourier transform of e to the power of minus j omega c t times u of t would be 1 over j omega plus omega c plus pi times delta omega plus omega c. So, on this basis cos omega c t u of t will have the Fourier transform 1/2 of pi delta omega plus omega c plus pi delta omega minus omega c because of the multiplication by this. In addition, you have 1 over j omega minus omega c plus 1 over j omega plus omega c. You put all these terms together, you can show that this will be equal to pi upon 2 delta omega minus omega c plus delta omega plus omega c, two delta functions, plus j omega by omega c squared minus omega squared. So, the spectrum would be like this. At omega c and minus omega c, you have delta functions. Of stance pi upon 2. In addition, you have a continuous variation of the magnitude corresponding to omega over omega c squared minus omega squared. So, something like this it will be. You observe that we are not taking a pure cosine wave lasting from minus infinity to plus infinity. If it had been a cosine wave lasting from minus infinity to plus infinity, there is only one single frequency term that is present, therefore, you would have spikes at plus omega c and minus omega c. This is not a pure cosine wave, it is cut off for negative values of t. Therefore, it is not a periodic phenomenon lasting from minus infinity to plus infinity. Therefore, you have other frequency components, not only the infinite the coefficient density at plus omega c and minus omega c, plus the a continuous band of frequencies with various magnitudes as shown in this. In fact, you can show that if I have a cosine omega c t ut, you can think of this as the sum of a cosine function which lasts forever, this is half cos omega c t, plus the same function repeating for positive half, and but the negative of this occurring for the negative t. So, this is cos omega c t divided by 2 multiplied by Signum function of t. So, it is this part which contributes to the delta functions. It is this part which contributes to this term. So, the delta part will correspond to this, and this continuous frequency is delta. So, that is how it goes. So, a pure cos omega c t ut, if it is a cos omega c t as such without multiplication by ut, it would have been pure impulses at these two frequencies, but because it is not periodic function in that sense lasting from minus infinity to plus infinity, you have an additional portion of the spectrum like this. Similarly, you can derive the spectrum for sin omega c t ut, but we will not do that in this. I will leave that as an exercise for you. We will discuss one additional property in this lecture, which relates to the convolution. You recall that the convolution of f of t, two time functions f of t and g of t, have been defined to be f of t minus x g of x dx from minus infinity to infinity. So, this is a function of time, and this is defined in this manner, f of t minus x g of x dx. The physical meaning of convolution, etc., we have discussed earlier. Let us try to find out the Fourier transform of this in terms of the Fourier transforms of f of t and g of t. So, the Fourier transform of f t gt convolved with gt can be written as minus infinity to plus infinity of e to the power of minus j omega t times this is the function of time now, minus infinity to plus infinity of f of t minus x g of x dx. This is the function of time, the new function of time dt. This is what the Fourier transform of this would be. This is integration with respect to time t, this is with integration with respect to x. Now, let us interchange the limits of integration. This is t from minus infinity to plus infinity, this is x from minus infinity to plus infinity. Let me interchange the limits of integration. Let us interchange the order of integration. I would like to do integration first with respect to t and then later with respect to x. So, all terms which are independent of t can be put outside. Therefore, I put gx dx, and those which are dependent on t I will put inside the first integral, which is to be done f of t minus x e to the power of minus j omega t. Now, from the property of translation in the time domain, if f of t has a Fourier transform of f of j omega, when you have f of t minus x, the Fourier transform of this we know is f of j omega multiplied by e to the power of j omega x. So, this turns out to be x from minus infinity to plus infinity of gx dx e to the power of f of j omega multiplied by e to the power of minus j omega x. And in this we are integrating with reference to x, therefore, I can write this as f of j omega can be pulled outside the integration sign, and then you have minus infinity to plus infinity of g of x e to the power of minus j omega x dx, which is the standard formula for the Fourier transform of g of t. Instead of t I have put x, is a dummy index, therefore, this is indeed g of j omega, therefore, f of j omega multiplied by g of j omega is the Fourier transform of this. So, that is a nice result in the sense that you have the convolution in time domain corresponds to multiplication in the transform domain. So, f of t convolved with g of t, which is a complicated integral operation, is carries over in the frequency domain or the transform domain as pure multiplication of the two time functions. So, convolution in the time domain corresponds to multiplication in the transform domain. This has very interesting applications in system and network theory, which we will come across as we go along. And in the convolution formula here, when you take the apply this to Fourier transforms, Fourier transform theory, all functions of time are assumed to be lasting from minus infinity to plus infinity. So, the limits must be taken from minus infinity to plus infinity. This may be different when you go to Laplace transform later on, but as far as the Fourier transform theory is concerned, the convolution you must take from minus infinity to plus infinity. And two time functions which are convolved in time, as far as the transform domain is concerned, it is equivalent to multiplication in the transform domain. In this lecture, we first of all looked at the Fourier transforms of periodic functions of time. To start with, a pure DC will have in the Fourier transform a spike, that is an impulse at the origin, and Fourier transform is 0 everywhere else, indicating that the concentration of energy is only at one frequency, that is at DC. Then we took up a sinusoidal function of time, angular frequency omega naught, and we found in the Fourier spectrum we have two delta functions at plus omega c and minus omega c, and therefore, the spectrum consists of two impulses sitting at these frequencies plus omega c and minus omega c. That means there is no energy at all other frequencies. We extended this concept to a periodic function of time, which admits a Fourier series representation. In the Fourier series, the spectrum consists of lines having a finite amplitude, that is the various coefficients, Cn coefficients, and this is a line spectrum in the case of a Fourier series. But in the case of a Fourier integral, it continues to be a line spectrum because the energy is only at discrete frequencies. But now, since we are talking in terms of coefficient density, the line spectrum consists of a series of impulses sitting at these various discrete frequencies, and each impulse is strength of each impulse is related to the Fourier coefficient in the Fourier series representation by a factor 2 pi. That means, instead of C naught in the Fourier coefficient, we have 2 pi times C naught being the strength of the impulse in the Fourier spectrum. After having dealt with the periodic functions of time, we looked at functions of time like the unit step function or a sinusoidal function which lasts only for positive t, and then try to look at the Fourier spectra of these. We notice that this is not a pure periodic phenomena, this has an aperiodicity attached to it. Therefore, you have in the spectrum concentration of energy at one or more discrete frequencies corresponding to the basic character of the time function. If it is a unit step function, the concentration of energy is at DC. If it is a cosine omega c t ut, then the concentration of energy is plus omega c and minus omega c. But since these are not periodic functions, they are cut off for negative values of time. You have also a portion of the spectrum which is continuous and which is representative of an aperiodic function. Therefore, you have a continuous spectrum as well as one or more lines representing the particular frequencies which are present. We saw that in the analysis of such functions, the Signum function plays an important role. Signum function is one which has got -1 for negative t and +1 for positive t, and we saw a Signum function as the Fourier transform 2 upon j omega. Lastly, we looked at the convolution property in the time domain and how it is goes over in the transform domain. Two time functions f of t and g of t, when they are convolved in time domain, in the transform domain the resulting function of time will be having a Fourier transform which is the product of the Fourier transforms of the individual components which are convolved together. In particular, f t star g t, which is the convolution of f t and g t, has a Fourier transform which is f j omega times g f j omega. This particular property is very useful in network and system studies, as we will see later, and in the next lecture we will start off with an example illustrating the convolution property, and we will go on from there.